Good morning and welcome to all of you. In today's class, we are going to discuss about the static magnetic field. There are three sources of magnetic field. One is permanent magnets, second one current carrying conductor, and the third one is time varying electric field. So magnetic field obtained by the permanent magnets, we are not going to discuss about the magnetic field that is created by the permanent magnets. Magnetic field created by a time varying electric field. This will be discussed afterwards. Right now, let us concentrate on the magnetic field that is created by a current carrying conductor. The magnitude and direction of the magnetic field intensity obtained by a current carrying conductor is explained by Biot-Savart law. Biot-Savart law is also known as Ampere's law for the current element. For example, let us consider a thin conductor carrying a current of I in this particular direction. If I consider a differential length dl of the conductor, this also carries a current of I. So IDL is a differential current element. IDL is a differential current element. So due to this IDL, at a given point P, what is the magnitude and direction of the magnetic field intensity? Assume that the distance from dl to point P is r. This is the direction of the current. The differential magnetic field intensity at point P due to this differential current element IDL is given by dH is equal to IDL sin theta by 4 pi r square. So the magnitude of dH is equal to IDL sin theta by 4 pi r square. What is theta? Theta is the angle between dl and r. So this is the direction of dl, this is the direction of theta, so this is the direction of r. So this angle will be theta. Suppose if the current flows in the reverse direction, then this would be theta. The direction of the magnetic field intensity is perpendicular to the plane containing both dl and r. So if you can imagine a plane surface that contains both dl and r, the direction of the magnetic field intensity is perpendicular to both dl and r. And in fact, to determine the exact direction, you place a right-handed screw at point P where we are defining the magnetic field intensity. Turn the screw from dl to r. If I turn the screw from dl to r, in this case it is an inward normal. So that gives you the direction of the magnetic field intensity. So in general, in whatever direction the screw progresses, when you turn the screw from dl to r, that would be the direction of the magnetic field intensity. So dH is given by IDL sin theta by 4 pi r square, that is the magnitude of the magnetic field intensity, and direction of H is perpendicular to both dl and r. Suppose if I want to combine the magnitude and the direction using a single expression, what we can do is, if I define a unit vector AL in this direction, along the direction of the current, and AR is a unit vector that is directed from dl to point P. It is always towards point P. What is AL cross AR? AL cross AR is equal to magnitude of AL into magnitude of AR into sin theta. So its value is sin theta. What is the direction of AL cross AR? Turn the screw from AL to AR. So this is nothing but the direction of DH. So DH is equal to IDL by 4 pi r square, and sin theta and the angle, or actually the sin theta and the direction of DH is now taken care by AL cross AR, because when you expand AL cross AR, it is sin theta into direction of DH, which is perpendicular to both DL and R. So using a single expression, now I can define DH is equal to IDL by 4 pi R square AL cross AR. Both magnitude and directions of DH have now been defined using a single expression. But what is DL into AL? It is vector DL. So DH is equal to IDL cross AR by 4 pi R square. Now let us consider what is the magnetic field intensity at a given point P due to a straight conductor carrying a current of I. Let us say in this direction it is carrying a current of I. Assume that the conductor is placed along x-axis, point P lies on xy plane, then the perpendicular distance from point P onto the conductor is, let us say, h, and point P is making angles of alpha 1 and alpha 2 with the ends of the conductor. This is alpha 2. Now, what is the magnetic field intensity at point P? So, for this, what I'm going to do is, because the conductor is placed along x-axis, I can divide this into small segments, differential lengths. Each can be described as dx. So, when I consider one such dx, which is carrying a current of I, so I dx is the differential current element. From dx to point P, let the distance is r, and this angle is theta. So the idea is, if you can find out what is the differential magnetic field intensity at point P, because of this differential current element IDX, we get one expression. When you integrate that expression, you get the total magnetic field intensity. So from Biot-Savart law, what is the differential magnetic field intensity at point P because of this differential current element IDX? It is equal to IDX sin theta by 4 pi r square. What is theta? Theta is the angle between dx and r. What about the direction of the magnetic field intensity? So once we assume that point P lies on xy plane, all these lines, the line joining point P to one end of the conductor, this H and this R, and the line joining point P to the other end of the conductor, all these lines will be lying in the xy plane. So when I turn the screw from dx to r in the anti-clockwise direction, the screw progresses along that direction. So that is the direction of the magnetic field intensity. So DHZ is given by IDX sin theta by 4 pi r square, or DH is equal to IDX sin theta by 4 pi r square, and the direction is along Z. So if this is the differential magnetic field intensity at point P because of the differential current element IDX, what is the total magnetic field intensity? I need to integrate this expression. So integral dHz is equal to Hz is equal to I by 4 pi integral dx sin theta by r square. So when you integrate this expression, I have to go from one end to the other end of the conductor. So when you go from one end to the other end, you can see that x is variable, theta is variable, r is also variable. So what we can do is, if you can write this dx and r square in terms of theta, then you will be having only one variable and you will be able to perform the integration. So remember that in order to perform the integration, there has to be only one variable. So let us try to write dx and r square in terms of theta so that we can perform the integration. Once point P is fixed, the perpendicular onto the conductor, this point is also fixed. So the distance from one end of the conductor to this point, it is fixed. Let us define this as L1. So once point P is fixed, L1 is also constant. So this distance is x. So naturally this distance must be L1 minus x. So when you take this triangle, What is cot theta? Cot theta is equal to L1 minus x divided by h. Cot theta is equal to L1 minus x divided by h. So L1 minus x is equal to h cot theta. So if I differentiate both sides, dx is equal to minus h cosecant square theta d theta. So when you cancel out that minus sign, the dx is equal to h cosecant square theta d theta. In the same triangle, what is cosecant theta? R by h. So what is R? R is equal to h cosecant theta. So let us go back to this expression. Hz is equal to I by 4 pi dx. Dx is h cosecant square theta d theta into sine theta by r square. R square is h square cosecant square theta. So we get this as I by 4 pi h integral sine theta d theta. Now that there is only one variable theta, we can perform the integration. What are the limits of theta? When theta is equal to alpha 1, we get one end. When theta is equal to this one, pi minus alpha 2, we get the other end. So the limits are going to be alpha 1 to pi minus alpha 2. So finally, the expression for h, which is along z direction, is given by I by 4 pi h cos alpha 1 plus cos alpha 2. Now let us consider an infinite length conductor placed along z direction carrying a current of I in the positive z direction. So because it is infinite length conductor, the limits of z would be minus infinity to plus infinity. Z is minus infinity to z plus infinity. It is carrying a current of I in the positive z direction. At a given point P, which is at a distance of rho meters, what is the expression for the magnetic field intensity in cylindrical coordinates? That means we need to express the magnitude in terms of rho phi z and the direction of the magnetic field intensity in terms of a rho, a phi, a z. Now what I am going to do is, let us consider at a distance of z meters above this z is equal to 0 plane, xy plane, z is equal to 0 plane, let us consider a differential length dz. This carries a current of I. So I dz is a differential current element. So the idea is, if you can find out what is the magnetic field intensity, differential magnetic field intensity at point P because of this I dz, you get one expression. Integrate that expression with the respective limit z is equal to minus infinity to z is equal to plus infinity, so that you get the total magnetic field intensity. Now, due to the differential current element IDZ at point P, what is the expression for DH? From Biot-Savart law, ideal cross AR by 4 pi r square, both magnitude and directions can be expressed using the single expression. Now that ideal becomes IDZ cross AR by 4 pi r square. What is R? The distance from DZ to point P. What is AR? Unit vector defined along the direction of R. So DH is equal to IDZ cross AR by 4 pi r square. So because we ultimately want an expression in cylindrical coordinates, we need to express this R square and the unit vector AR in cylindrical coordinates. That means R in terms of rho phi z and the unit vector AR in terms of a rho a phi a z. So for that, we have this expression ZAZ plus vector R minus rho a rho is equal to 0. ZAZ plus vector R minus rho a rho is equal to 0. So what is vector R? Rho a rho minus ZAZ. So what is the magnitude of R? Root of rho square plus Z square. The unit vector AR is given by vector R divided by its magnitude. So let us go back to this expression. DH is equal to I dz. So I vector dz means dz az cross unit vector ar divided by 4 pi r square. So ultimately we get this as I into dz into rho a5 by 4 pi rho square plus z square whole to the power of 3 by 2. So indicating that the direction of dh is 5. So if I want to find out what is the total phi component of h, I need to integrate this one. H phi is equal to integral dh phi, which is equal to I into rho by 4 pi integral dz by rho square plus z square whole to the power of 3 by 2. What are the limits of z? Minus infinity to plus infinity. So we just have to evaluate this integral. Of course, there are several ways of evaluating this integral. One way is, if I define this angle as theta, what is tan theta? Z by rho. So what is z? Rho tan theta. So if I differentiate both sides, dz is equal to rho secant square theta d theta. What is rho square plus z square? Rho square plus rho square tan square theta. So rho square secant square theta whole to the power of 3 by 2 means rho cube secant cube theta. So this expression becomes I by 4 pi rho integral cos theta d theta minus pi by 2 to plus pi by 2. So finally h phi is equal to I by 2 pi rho, or h is equal to I by 2 pi rho a phi. Now if you look at the direction of the magnetic field, it is phi. That means it is a part of the circle. So whenever you want to represent a part of the circle, dl is equal to rho d phi a phi. So indicating that the magnetic flux lines are closed lines. So if you take any circle, the magnitude of h at every point on the circular line is constant, because at any point on the circle, if you drop a perpendicular onto the conductor, it is rho. So once rho is constant, magnitude of h is constant, and the direction of a phi indicates that it is a circular line. So one of the main differences between electric flux lines and the magnetic flux lines are, electric flux lines are closed, not closed lines, but the magnetic flux lines are closed lines.